Okay, so now I'm going to talk about Floquet theory. How many people have, oh, I can put this right. How many people have heard of Floquet theory? No? How many, yes? How many people feel comfortable with Floquet theory? How many people, well, I guess nobody's going to answer this. Say, what do you mean by comfortable with? Am I going to be asked to do a problem on the board? No, because you can't do anything analytically with Floquet theory, so you're safe from that. Okay, how many people have never heard of Floquet theory? And how many people have heard of it but don't know what it is? Okay. So I was in that position for many years. But it turns out it's very, very easy. Okay, everybody knows how to solve linear equations with constant coefficients, right? Everybody knows that an equation like this, it acts like it is a combination of exponentials, and the exponentials are to be found by solving a quadratic equation for that exponential. And that applies as well to trigonometric functions. And you know that this is true for any degree. That is to say, if it was if you had a first order differential equation, you would have a single exponential, which in fact that's the thing that we use all the time, right? And if you had more than a second order, I mean, we tend to do second order because quadratic equations are the most complicated thing that we can do easily, but this is true in general. Even if you can't solve the nth order polynomial equation, if you have an nth order differential equation, then it is a sum of n exponentials where the lambdas obey an nth order polynomial. Okay, so everybody knows this. And Floquet theory merely generalizes this a little bit, and it's really easy because, as I said, you can't do anything analytically, so you only need to learn the next 2 lines, and then after that you can't do anything anyway with pencil and paper, so you've learned it all. Okay, so the next most complicated thing, you might not think it is, but it is to have, instead of constant coefficients here, you have periodic coefficients. This A, B, C are not numbers, but are functions of the independent variable, which here is time. So you have A of t, which is really a function of t mod t, and B and C, these are all periodic functions. And the generalization is that the solution is, yes, a sum of exponentials times periodic functions. Periodic functions with that same period. This is really it. This is, to me, well, I suppose there's more to it, but this is really what I know of Floquet theory. It's taking this green and blue line here to this green and blue line. You cannot find the lambda 1 and lambda 2 analytically. That's why I say you really can't go any further. That's why it's so easy to learn, because you can't do anything more. Then there are names. These things, the lambda 1 and lambda 2, are called the Floquet exponents. These alpha 1 and alpha 2, which are functions of that same period, that t periodic functions with that same period as the coefficient functions, they're called Floquet functions. And then if you take e to the lambda 1 capital T, that's called a Floquet multiplier. And that is pretty much it. So that's what's written here. The Floquet exponents are not roots of a polynomial. They must be calculated numerically or asymptotically, and this is true in general. If you have a first order equation with a time periodic coefficient, then it is an exponential times a function which is periodic, and it's true for any order.
Excuse me.
Yes.
It's essential that all 3 have the same period, or the 3 can be periodic with different
No,
periods?
it's essential that they have the same period. If you want to do this, I mean, perhaps they have one common period. Perhaps their periods are rationally related or something, in which case this would be true for that common period. But yes, they have the same period. So we can do dynamical systems with Floquet theory. Here's our dynamical system, x dot equals f of x. Suppose we have a limit cycle as a solution. We have an x bar, which is not a fixed point, but an x bar such that you translate by time t, you get back to the same thing, and it satisfies the differential equation. Supposing we're interested in the stability of the limit cycle. So we write x of t as x bar of t plus epsilon of t. And now let's substitute this into the differential equation, the dynamical system. We have x bar dot plus epsilon dot. Before we didn't have an x bar dot because we had fixed points only. We were looking at the stability of fixed points, not the stability of limit cycles. But now we have an x bar dot. And now we'll do the same Taylor expansion. Our epsilon is small, infinitesimally small, such that we assume it's small throughout time. We have f of x bar of t, and usually we've set that equal to 0 because we had a fixed point, but we don't have a fixed point anymore. X bar dot is equal to f of x bar of t, so these two cancel each other out, and we get the linear equation, epsilon dot equals f prime x bar of t, epsilon t. Why is this a linear equation? People often, I feel people misuse the word linear. They use it to mean all kinds of things. This is not a linear function of x necessarily. It's not a linear function t. What is linear about this? It's that epsilon appears once. Not 0 times, not 2 times, but once. That's what makes this a linear differential equation. And this is an equation of Floquet form. This is where many Floquet problems come from. You might say, why should I have a coefficient function which is periodic in time? Why? Because you see that here. You see that as you've taken the derivative of the limit cycle, this thing here has period t, capital T. So this is a Floquet problem. The stability problem for a limit cycle is a Floquet problem. And therefore, the solution is a Floquet form, which is to say that epsilon, the perturbation, its behavior is an exponential times a periodic function. And so although you can't calculate these things analytically, still it's very helpful in organizing your thoughts. You know that this periodic function cannot grow, it's periodic. So it can neither grow nor decay, it comes back every t to where it was. What can grow or decay is the exponential. So you're interested in the sign of the Floquet exponent, or rather its real part. Okay, so just as before, you're just preceded by this function which you don't know. And then this is the picture I was trying to draw here. I was saying that the Floquet exponent, you're interested in whether it is, it has positive or negative real part. And if you take the exponent of that, the exponential of that, you get the circle. And what is my point? Yes, I knew there was, I was a little bothered by how I had to stop here. But here I think I'm saved because how to divide this function, how to divide it into an exponential and a periodic part. That's easy if this is a real exponential, okay. But supposing it's a complex exponential, supposing it has a trigonometric part, then this decomposition is not well defined. There's a piece that could go into the lambda, if there was an imaginary part, and a piece that could go into the alpha, right? The only way to make it well defined, it's like the tan function, right? You have to make it well defined by restricting it. So we restrict the imaginary part of the exponential to be between pi I over capital T and minus pi I over T. And then the rest of it goes into the periodic function, so as to just define it well. And that is when you see that this could be, no, I don't know, I still didn't figure that out. We'll just leave that as it is, right, okay. Yeah, so that's our choice to make it unique. There are other terms, but all of them have to be done numerically. So it's the monodromy matrix is a matrix that you, a time-dependent matrix that you get by integrating the linearized problem. And this is the eigenvalues of the monodromy matrix are the Floquet multipliers. I think maybe that's pretty much, yes, that's all I wanted to say that was theoretical. Now we're going to look at two cases of Floquet analysis. One of them is Faraday waves and the other is cylinder wave. So Faraday waves, these are the standing waves that result from oscillating a thin layer of fluid. This is Faraday at a sketch, schematic sketch. He discovered, yes, oh no, you were saying. He discovered them in 1831. Undoubtedly, people had seen this before, but this is the first scientific study of these waves. And in the 1990s, it was discovered that you could form not merely simple patterns like stripes, squares, and hexagons, but also quasi-patterns. These are 12 pentagons organized around a book. And that was in 94, and this was followed by lots and lots of other quasi-patterns. In fact, here, let me show you. Just a second. Yeah, they found things that were these quasi-patterns that were as complicated as this. This is Arbel and Feinberg, and by oscillating with two different, slightly more complicated than one. This goes back to what you asked. This is with two frequency forcing, but they're rationally related, so they have a common period. It's just not a trigonometric function. It's a periodic function, but not but a sum of two trigonometric functions. Anyway, by varying that, these two axes are the amplitude of one of the trigonometric functions, and this is the other trigonometric functions. And you see that you get squares if you only do a trigonometric function, but if you do something more complicated, if you combine the two different trigonometric functions, you can get all kinds of weird things, as they did.
Do you still get patterns if they are not rationally related?
I believe so. I think so. I think so. Somebody must have looked at that.
Periodic flow, that theory I don't think exists yet, does it?
I've
I've heard it alluded to,
I've heard.
but that's not the same question as whether you get the same
But
patterns.
Cloquet theory is not about what patterns you get.
No.
Cloquet theory is a linear theory. It doesn't tell you anything about the patterns. The patterns tell you that's the subject of. In fact, I'm going to take a poll to remind you to do this about what I should do for the other classes. Whether you get squares or hexagons, the simplest pattern dynamical question, is governed by the signs of various nonlinear terms. As we saw last time for the standing versus traveling waves, it's in fact just the same kind of questions. And that's not governed at all by this linear stability. Linear stability is looking only at the wavelength, and so you can have a superposition. Pattern formation is how do functions with how do plane waves combine to form various patterns. But this is only telling you about the plane waves, only telling you about the wave numbers. Okay, so we start here, here, here. Okay. How has Faraday treated instead of acting as, numerically it would be very difficult to have or theoretically to have a boundary plate that moves. You have your boundaries that are functions of time. So no, you do all this in the frame in which the boundary is stationary, and so you put in an oscillating gravity to compensate for that. And those results with quasi-patterns were done by putting two different frequencies, two different temporal frequencies, thus eliciting two different spatial scales. Okay, so let's go to the how we reduce this to Cloquet analysis. We make the very often practiced assumption in hydrodynamic stability theory that we are dealing with an infinite horizontal layer, and thus we call them symmetry. That's what we did on Friday. There are no special points. Right? As soon as you put boundaries on, there are special points because you're going to be near the boundary or far from the boundary. So even if your boundaries are quite symmetric, even if you have a nice square boundary, this point is not the same as this one, is not the same as this one, is not the same as this one. So the easiest thing to do is to assume infinite horizontal extent and impose periodicity in space, or not necessarily impose, but seek solutions that are periodic in space. And that they will be because, in fact, this has to do with what we did just before. because if all points are the same in space, then it's constant coefficient in space. That's what symmetry means. If you were to have boundaries any place, then all points are not the same, and so your spatial problem is not homogeneous. It's not constant coefficient as far as space is concerned. Different points in space are different. If you're horizontally infinite with all the points being the same, it's like having constant coefficient equations, and therefore it is perfectly legitimate, and it's not, people often say an Ansatz, that is to say, which is the German word for an intuition or something. But it's not an intuition, it's an actual mathematical result that your solutions are exponentials. It's just as true as the fact that these solutions are exponentials here. So let's do that. Let's seek solutions of the form e to the I k dot x. They could be growing exponentials. Nothing prevents that except for the fact that we wish to study solutions that actually are bounded and don't go off to infinity. So trigonometric functions, e to the I k dot x, plane waves, we study them because they're the simplest thing to study, and that is actually legitimate to do. So we write the height as a plane wave, that is the dependence in horizontal dimensions, times a function of time. And putting in an oscillating gravity means that the height, or for every k, for every spatial wave number, this height obeys a temporal Cloquet problem with the period of the forcing. And hence the solution is of the form an exponential times a function. And why are there all these indices? Well, one of the indices comes from imposing a spatial wave number here. You can put it in which you can study whichever one you want, so that's that k. And the other one, the j, that comes from the fact that it will turn out to be a second order equation in time, and hence j is 1 and 2. In the case of no viscosity, it reduces to the math equation. This is the math equation. This is kind of the prototype of Cloquet analysis. You'll find it in many applied math books. What we're interested in is when the real part of these exponents cross 0. And what does that mean? When that happens, that means that plane waves, e to the I k dot x, grow. On one side they grow, on one side they decay. Meaning you have instability to that wave number. And this is like what we did for convection. You can consider this whole Faraday problem to be decoupled as far as every k goes. And what you're interested in is, does it do perturbations with all wave numbers decay, or does there exist a wave number k for which there is growth? If there exists a wave number for which there is growth, then it is unstable, and that is the wave number that you are likely to see. Okay, so, and in fact, now we can look at that's the real part. The imaginary part, it turns out that when the real part crosses 0, the imaginary part, we don't have that third part where they cross the circle at complex conjugate pairs. You can cross, okay, this is, again, another instance of a continuous dynamical system becoming a discrete one because you have a limit cycle, because you may have a flat surface, but you have this oscillating gravity, so you have time dependence, and if you sample it every moment, every period, it's a discrete system. And hence, you have these two possibilities of bifurcation through 1 and bifurcation through -1. If you have bifurcation through -1, then that is when the period becomes twice as long. Instead, you had forcing that was, you had your layer that was, you were doing, your layer is doing this, and then okay, if it's the same response, then that's what your surface is doing. But if your period can be twice as long, in which case it looks like this. And neither seems unrealistic. You don't think the system doesn't want to do this, but you see that the period of this is twice as long. My layer goes up. Sometimes my layer goes up and I'm here, and sometimes my layer goes up and I'm here. So the period of my response is twice the period of my forcing. And that's an example of one of those period doubling bifurcations. You don't quite see it that way because initially the system is periodic in a kind of trivial way. It's just you've gone into this oscillating frame. It's not as if the system was doing that. You were doing that. But anyway, the response is twice the period, and that's called then subharmonic. And those are the possibilities. And this is the solution to Matthew's equation. This is K, and this is the A as in the amplitude of the forcing. And this is subharmonic, harmonic, subharmonic, harmonics. Okay, so let's look at this in more detail. Over here, you have two eigenvalues, right? We said 1 and 2, because it's a second order differential equation. You have 2 of them. And this is with no viscosity, and hence it's a conservative system, and you can write that the sum of the eigenvalues is 0, or the product of the Cloquet multipliers is 1. And you can see those are the same things, e to the lambda 1 t times e to the lambda 2t. If lambda 1 plus lambda 2 is 0, that gives you 1, right? Okay, so here, in this next picture, we look at the Cloquet multipliers. And they are, at this point, we're going to just change the parameter. And the parameter here is k, the wave number which we are testing. We're testing to see do perturbations with wave number k grow or decay. And here, okay, these are meant to be one on top of the other. They're not meant to be sticking out. And so they neither grow nor decay, they're marginal. Now, as you change this k parameter, those two eigenvalues separate, and they have to separate in such a way that their product remains 1. You can see the product of this is 1, it's minus 1 times minus 1. The product remains 1. And the one that becomes less than minus 1, well, it causes growth. So there's growth inside here. And with this set of parameters, there is growth. K, waves with these values of k, subjected to this acceleration here, grow. As you continue looking in your parameter space, these two values come back, and they hit 0. They hit minus 1 again. In here, then, there is no growth. There is no growth because, and the multipliers travel along the circle, and they get here, and they're complex. They're not growing. They're on the circle, and then they keep going, and they meet at 1, and that's what's happening here. They meet at 1. And now they're going to do the same thing. Once they meet at 1, they separate. 1 becomes greater than 1 and 1 less than 1. And then you enter a harmonic tone, one where the response is 2. Over here, for those cases, the response was, okay, and so on and so forth. Okay. So, and this is the solution to Matthew equation, and it was found in 1954 by Benjamin and Ursel, that the inviscid Faraday problem mapped exactly to the inviscid Faraday problem mapped exactly to the Matthew equation. And the Cloquet functions, one rarely looks at them, but the Cloquet functions, remember, they're here, and there's going to be one for every k and for every j. We're only interested in the growing j, and anyway, for three, we could look here, here, and here for 3 different values of k, and here's what they look like. So you see, this is a periodic function with period. It's subharmonic. It has period. This is little t over big T, and it has period 2. This one has period 1, and this one also has period 2. But you see, it has three maximums, so we call it a 3-has time. And then, so that's the end. Okay, we did numerical simulations of Faraday instability, and I'm going to talk more about that this afternoon in colloquium. Right, okay. Now we're going to go to the cylinder weight, another Cloquet problem.